Hi everyone, I am Summaya and I'm working as a research fellow at Department of Informatics. I am also associated with SIRIUS Center for Scalable Data Access in Oil and Gas Industry. We have 12 industrial partners and we also have linked with 3 leading academic institutions. The main objective of our center is to provide solutions for complex problems in oil and gas industry. The research focus of our center is semantic technologies, database integration, data science, and industrial digital transformation. My main research focus is on knowledge-based systems. Currently, I am working to develop machine learning models that can take domain information into account. The first figure you see here it shows a standard machine learning system, and we experimented in different settings to see that the performance of the complex system is not good when we follow this standard pipeline. And the main reason here is that the systems that are developed for critical scenarios, they don't incorporate the domain information into the systems. They only have the training based on the structured data or the data that we have from past, and in some scenarios it may not account for all the information of a domain, or we may not see all the data points. So in order to improve the performance and also to build systems that are reliable in long term, we want to utilize the domain information. And also after building our model, we want to match it with the human experts. So before deploying, our main focus here is that we kind of use this domain information in our learning process. And after a model is done, we can take feedback from the actual experts who need the system. And if there is some kind of disagreement between a human expert and the model, then how we can alter the model to take this information into account and create better models. So I have been working in adding information in both supervised and unsupervised setting. But today I'll just discuss how we can use the structured domain information in a unsupervised fashion. So today's presentation will focus only on adding knowledge in textual data, particularly for categorical data in machine learning, and how we can use our structure information to learn similarities between our different categorical values. And first, I'll explain industrial use case to tell you details about the complexity of different real-world problems, and then I'll go through the details of the proposed method. So the main use case here is when we are in oil and gas industry, we want to find out where is an oil field. And this is a very important question because before drilling or before starting planning of an oil field, it is important to answer this question that what are the location where we will be able to find an oil field. If you look at the overall timeline of an oil field, you can see that there is a 5 to 10 years duration only in the exploration phase where the companies try to answer this question, where can we find this new oil field? But this is a very complicated task because the domain itself is very complicated and there are many inherent dependencies in this domain. For example, if we look at cross section of an oil field, so you can see that there is many layers inside Earth. And if we see here like upper Cretaceous and lower Cretaceous, these are the layers that are close to each other. And we have an oil window, and then in layers beneath the oil window, we have a gas window. And if we look at the rock types inside the Earth, so we see here that we have different rock types as well. So when we convert this information into a relational database, this is all the information we have. So we have a textual information or categorical data, So we have geological time period, rock type, and some other properties of the oil field. The biggest issue is that there are many types of different geological times here and rock types here. So when we transfer our domain information into this relational database, uh, then a lot of information is lost here. We don't see the links between the layers inside the earth. We have this information that what are the different names of the layers inside the earth, but we don't have this information that how these layers are connected with each other. And if you want to apply machine learning directly on this textual data, then we are missing a lot of characteristics, a lot of the inherent things that are there. So the key idea here is that we can use existing information that the scientists have developed. For example, if we want to answer this question, where is an oil field, and if we are looking at rocks that are present there, then we know this information that there are different type of rocks in the world. For example, if we have sandstone and siltstone, these are both clastic rocks and they will have similar characteristics. So all the oil fields that have this kind of sandstones, they have similar quality of reservoir oil and gas or any other hydrocarbon. But if we have like two different kind of rock types, we will have totally different type of hydrocarbons there. Also, if we look at different geological time periods, we can see here that we have this information that inside Jurassic time scale, we have upper, middle, and lower categories. And these are all related. When we will move from Jurassic into a Triassic age, we will have different characteristics here. So the idea is that we have this information that is already placed in a very nice format. Can we link this information with our traditional machine learning process, specifically in complex domains where we don't have so much data or the data is too complicated to be directly fed into a machine learning process? So these are the overall objectives of this method. That the most important thing is that we want to consider the inherent dependencies that we have in complex domains like oil and gas or medicine. And then we want to find the semantics between different textual data. We want to find the semantic link between different categories. If we have two rock types, we want to see how semantically similar these things are. And our objective is that we want the domain information to find out this similarity. So the data set that we have used in this study is based on the oil fields in the world. We have 30,000 oil fields, or we can call it reservoirs. And then we selected two test fields. We already knew that the 15 similar fields for these two test fields. And what we want to do is we want to devise an algorithm that can give us recommendation for these top 10 fields. So what we are doing here is we will take one test field and then we will say our geologist to give us 15 most similar fields in the world to this field depending on the characteristics. And we will do the same thing with our machine learning engine, that we will ask the engine to recommend us 15 different fields. And then we will compare our results, how good our model is as compared to the experts who are working in the field. So traditionally what is being done in the machine learning community is that the textual information is encoded as one hot or embedded, but we are not interested to do this in this work. We are more interested to find the similarity measures for categorical data. And these are the existing approaches that are based on frequency-based measures. And what I mean by frequency is these existing measures, they mostly take into account how many times two things are occurring. For example, if I want to compare two values, x and y, in a simple matching thing, I will say if they are exactly similar, they have similarity of 1, otherwise it's a 0. And then there are different versions here that take the frequency of both things into account to find out how similar two concepts are in a domain. But these frequency-based measures they don't take into account the complexities of a domain, or they don't take into account the semantic similarities between two concepts. If x and y are not exactly similar, then we are interested to find out how much similar they are. If it is not one, maybe they are 70% similar or 50% similar, but we want to quantify this thing in a way that we can later on use on in our machine learning process. So the first step here is that we want to link our information that we have in this format with our traditional relational database where we don't have this information. So for example, if I take this value upper Jurassic here and the middle Jurassic, then from here we know that these are linked together into Jurassic. So now I know that whenever I'll have upper, middle, or lower Jurassic in the database, I can link it into a bigger categorization, Jurassic. Similarly, if I have a different time scale like Triassic, then we can see that they all upper, middle, and lower Triassic, they belong to Triassic environment, and later on we can sum them up as Mesozoic. So what is semantic similarity? So the first step we did is we took data from our tables and we put it into a structure where we can see how things are linked together in a domain. Once we have this basic information, now the next step is we want to find the semantic content of these concepts. And we can say that two concepts are semantically similar if they have some common information. For example, if I want to say upper and middle Jurassic, how much similar they are semantically, then I will see how much common information both of them have. So both of these concepts belong to a common parent class, that is Jurassic. Similarly, if you want to see lower Triassic and upper Jurassic, how common they are, so their common parent is Mesozoic. So they don't have a direct common ancestor that we can compare it with. So we want to utilize this key idea that if we have different concepts and we know how they are grouped together, we can use this information to find semantic similarity. And in a study conducted already by Resnick, the common information is represented as a lowest common ancestor. So if we have a tree like this that classifies our data into different concepts, so whenever we want to say that we want to find common information between two concepts, we can say that it is equal to the lowest common ancestor in a tree. So upper Jurassic and lower Jurassic are semantically more similar because they have an immediate lowest common ancestor. As we will move up in the tree, we will have less commonalities between different pair of values. So we want to say upper and lower Triassic, how much common they are, and we will look at their lowest common ancestor, which is Mesozoic, and it is far from the leaf nodes. So based on this idea, we proposed two techniques. One is we wanted to combine this domain information with the existing frequency-based information, and other is we only want to find the similarity based on hierarchy, not using any other information. So the first technique that we proposed is information content based semantic similarity. So here we are doing is we are saying two concepts x and y are exactly similar, then we say that their similarity is 1. Otherwise, if we want to look at the similarity between two concepts, then we will look at the information content of their lowest common ancestor. So x and y, we will look at the information content of their lowest common ancestor, that is Jurassic. And there are different ways to find the information content in a tree-like structure or in a taxonomy. which I'm not going into details. I have mentioned all these details in the relevant paper. The second technique is based on the only using hierarchy, where we don't want to look at the information content. We are just assuming that we have only this structure here and we know our concepts, how we can convert this information into numbers which we can later use on. So for comparing two things that are exactly similar, the similarity is same here, that is the maximum similarity of 1. But if two concepts are not similar, then we will look at their level of lowest common ancestor. D here represents the depth of the tree. So when we put values in this formula, the things that are close to the leaf nodes are the things that have lowest common ancestor away from the root. They will have high similarity. For example, upper and lower Jurassic here will get high similarity as compared to upper and lower Triassic. So for evaluation, we used a ranked list of recommendation based on our own technique, and then we got ranked list of recommendations from the geologist. So the standard way of evaluating a task in information retrieval is to find the ranked precision for the both lists that we retrieve from the scientist and from our own search engine. So here you can see the results of the techniques. We are comparing our technique with the existing frequency-based methods here that do not use any domain information. With the semantic-based methods, both HS and ICS, they are using the domain information. And for the two test cases that we selected earlier for evaluating our technique, we can see that we have a very high score of 66 and 59% for both oil fields. And this accuracy is not very high here, but the main thing here is that the factors that we are taking into account into our machine learning model in our recommendation setting is that we have only few properties and the domain information. And we are comparing this with the ranked list that is given by the geologists who have experience of 10 to 15 years in the field, and they have already experience of looking at various oil fields in the world, and then decide that if we get a new location, how many other oil fields in the world are similar to this. But in our similarity engine, we don't have all the information that the scientists have, like seismic and the simulations and the models. We just have our textual data and the domain information linked with our textual data that tells us how the concepts are interrelated. So for a machine learning model to give a 66% accuracy just based on the 4 to 5 properties and the domain information, this is actually pretty good as compared to the other frequency-based methods. So here you can see that for our field SNURA, the precision is less than 50%, and for SNUWIT, that is a very complicated field, it is even worse, it is 15%. But if we only use the hierarchy-based semantic measure between different concepts, then we can already see that for both cases we have 50 plus accuracy. So the main idea of this work is that if you have 30,000 oil fields, you can recommend your experts only 10 to 15 top similar fields, and then we leave the work to the geologists to just go through those 15 fields and analyze which are most similar fields or where they need to look at. So in this way, we can aid the experts to perform their work more efficiently by utilizing the domain knowledge. So the overall conclusion that we have is that we are using this lowest common approach in an unsupervised setting where we are just interested to find the list of recommendations. The results are significantly better than the existing traditional methods that do not take into account any kind of domain knowledge or knowledge representation. Also, we have ability to calculate similarity for unseen data points if you don't have any concepts that are in your relational database, but if those concepts are present in your domain information, then it's very easy for you to calculate similarity between all the concepts that are in your domain, and you can use it in future as well if you don't have the points so far in the training set. Thank you everyone for listening to the presentation, and we still have some time left, so if you have any questions, please feel free to ask.